Hello there, so it's time for another credible news story. This link comes from https:// www.liverpoolmuseums.org.uk. This is read aloud so that you can be hands-free, and I am doing this as a non-professional without a license. Report me. Sorry. Anyway. This article is published by Patrick Kiernan, Education Demonstrator, Learning and Participation. It is titled, "Which is Greater, the Number of Atoms in the Universe or the Number of Chess Moves?" We explore AI's mind-blowing processing ability from winning chess to finding new galaxies. The question came from Claude Shannon, inventor of, quote, information theory, unquote, in 1948. The theory uses mathematics to understand the rules governing the transmission of messages through communication systems applicable to everything from computer code, speech and music, to the dancing of bees. Using maths and logic to understand the world around him, it wasn't long before Shannon began to wonder if a computer could beat a human at games such as chess. In 1950, he wrote a paper asserting this possibility, but it wasn't until the 1970s that computers began to defeat humans at the game, generally poor players who made silly mistakes. But they could not defeat grand masters. That did not happen until 1996, when Deep Blue beat Garry Kasparov. The following year, the improved Deep Blue beat him 31-2, 21-2. So why did it take so long? Remember the question at the start? Well, there are between 10 to 78 power to 10 to the 82nd power atoms in the observable universe. That's between 10 quadrillion vigintillion and 100,000 quadrillion vigintillion atoms, which is a lot. But amazingly, there are even more possible variations of chess games than there are atoms in the observable universe. This is the Shannon number and represents all of the possible move variations in the game of chess. It is estimated there are between 10 to the 111th power and 10 to the 123rd positions, including illegal moves, in chess. If you rule out illegal moves, that number drops dramatically to 10 to the 40th power moves, which is still a lot. Quote, there are even more possible variations of chess games than there are atoms in the observable universe, unquote. You might think, well, a computer has conquered the most complicated game in the world. There's nothing left for them to do. And you'd be wrong. There is a game with even more possible moves and variations, and it is called Go. Thought to have originated in China over 4,000 years ago, it did not become popular until it arrived in Japan around the year 500. It is played extensively in Southeast Asia. Professionals start learning the game as very small children and spend all their lives perfecting their ability. Go has more than 10 to the 170th power moves, making it a Google times more complicated and varied than chess, and dwarfing the number of atoms in the universe. Do you think a computer or artificial intelligence could ever master a game this complicated in your lifetime? Amazingly, it already has. Enter AlphaGo. In 2015, it played its first match against reigning three-time European champion Mr. Fan Hui and beat him 5-0. In March 2016, the AI then competed against legendary Go player, 18-time world title winner Mr. Lee Sedol. It said that Sedol is to Go what Federer is to tennis, yet, with 200 million people watching worldwide, AlphaGo beat him 4-1 in a competition in Seoul, South Korea. All Go players are ranked, An absolute beginner is ranked as Q30. As they improve, they move towards the rank Q1. As they continue to improve, they then join the Dawn ranks, starting at level 1 and aim for, but rarely reach, level 9 Dawn. There are currently just over 100 9 Dawn players in the world. AlphaGo is one of them. Narrator insertion here. There are 8 billion people on the planet. So a group of 100 might sound large, but out of a group of 8 billion, it's an infinitesimally small number of people. So that's 100 brains that are extremely smart. I guarantee you they're very valuable. All right, exiting out of narrator insertion. There's more. The company that created AlphaGo, DeepMind, released a newer, more powerful version, AlphaGo Zero. According to DeepMind, quote, AlphaGo learned Go by playing thousands of matches with amateur and professional players. AlphaGo Zero learned by playing against itself, starting from completely random play, and then by playing against the strongest player in the world, AlphaGo. This powerful technique is no longer constrained by the limits of human knowledge. Instead, the computer program accumulated thousands of years of human knowledge during a period of just a few days. Go Zero quickly surpassed the performance of all previous versions and also discovered new knowledge, developing unconventional strategies and creative new moves, including those which beat the world Go champions Lee Sedol and KG, unquote. Now you may think, quote, so what? A machine can play a game. Big deal, unquote. The big deal is that it has been able to make new discoveries, novel approaches. That AI can have, quote, creative moments, unquote, suggests that AI can be used to enhance human ingenuity rapidly. When dealing with vast amounts of information, when attempting to understand lots of data, particularly mathematical, the human mind can become overwhelmed and tires quickly. And AI doesn't have those problems. AlphaGo Zero learned thousands of years of human knowledge in just a few days. Applying that ability to other areas will allow patterns and discoveries that might otherwise be hidden or take a long time to discover by people alone. How does an artificial intelligence learn? It's a really good question, and it is both simple and very clever. There are 3 levels of learning for an AI: artificial intelligence, machine learning, and deep learning. Artificial intelligence is the lowest level of computer intelligence. It mimics human learning by making decisions based on options and checks, then with stored information. Is it round or curvy? Is it green or yellow? Is it a lime or banana? Machine learning comes from experience. Are all round green things limes? Can they be apples? Is it bigger than a certain size? Therefore, based on what it has learned from option choosing, it can say what the object is. Deep learning is a subset of machine learning. The software can train itself using hidden layers called neural networks to understand its outputs. This approach uses huge amounts of data as it requires the machine to check with its database or experience to find things it, quote, knows, unquote, already to allow it to identify objects. Quote, that AI can have, quote, creative moments, unquote, suggests that AI can be used to enhance human ingenuity rapidly, unquote. What has this got to do with astronomy? Well, I'm glad you asked. No, really, I am. Even though there are more moves in chess than atoms in the universe is still very, very big. It is estimated that there are 200 to 350 billion stars in our galaxy, the Milky Way. Our galaxy is a medium-sized galaxy. It's believed there may be over 1 trillion galaxies in the visible universe and many more that we can't see. Think of it this way. Next time you go to the seaside, grab a handful of sand or dig a hole in the sand. How many grains of sand do you think there are in your hand or in the pile you've just dug? Thousands? Millions, maybe? Now look at the whole beach and try to guess how many grains there are. It is thought that there are more stars in the universe than grains of sand on every beach on Earth. Most of those stars have at least one planet, often many more, orbiting. So there are even more planets than stars. Astronomers and astrophysicists deal with lots and lots of data, and as technology improves, the amount of data collected increases. There are many new telescopes and observatories under development and soon to come online, as well as the space-based James Webb Telescope and the extremely large telescope in Chile. There is also coming to Chile in 2021 the Large Synoptic Survey Telescope, or the LSST, also known as the Vera Rubin Telescope. When it begins operation, it will take more than 800 panoramic images each night with a 3.2 billion pixel camera, recording the entire visible sky twice each week. Each night, it will produce 20 terabytes of data. The images taken by the LSST camera are so large that it would take 378 4000K ultra high definition TV screens to display one of them in full size. How big is a terabyte, I hear you ask? 1 terabyte is the same as 681 episodes of The Queen's Gambit. One can dream. So much data, you say? You're right. It's far more than we humans can work on. That's just from one telescope. There are a whole variety of programs, AI, machine learning, and deep learning systems being used by astronomers and researchers. Because it is more than a human can cope with, trainable neural networks are needed to help with classifying objects and suggesting to astronomers those that might be interesting to look at more closely. The European Southern Observatory has developed Morpheus, a deep learning framework that incorporates a variety of artificial intelligence technologies developed for applications such as image and speech recognition. To help astronomers, Morpheus will work pixel by pixel through the images looking for galaxies. An older Morpheus result from 2016 working with Hubble revealed that here were 10 times more galaxies than previously thought. Quote, an older Morpheus result from 2016 working with Hubble revealed that there were 10 times more galaxies than previously thought. Unquote. Researchers at Lancaster University have developed a system called DeepC, Deep Learning for Galaxy Cluster Extraction and Evaluation, a novel deep learning technique to speed up the process of finding galaxy clusters. First discovered in 1950 by George Abel, galaxy clusters are rare but massive objects. Abel spent years scanning 2,000 photographic plates with his eye and a magnifying glass and found 2,712 clusters. Galaxy clusters are important as they will help us understand how dark matter and dark energy have shaped our universe. DeepC builds on Abel's approach, replacing the astronomer with an AI model trained to, quote, look, unquote, at color images and identify galaxy clusters. It is a state-of-the-art model based on neural networks, which is designed to mimic the way a human brain learns to recognize objects by activating specific neurons when visualizing distinctive patterns and colors. The AI was trained by repeatedly showing it examples of known, labeled objects and images until the algorithm learned to recognize objects on its own. DeepC will also be used on the Rubin telescope. Not yet finished, but with phase 1 already running, is the Square Kilometer Array, or the SKA, a series of radio telescopes that span continents and will be the largest ever radio telescope. Its headquarters are in Jodrell Bank in Cheshire. The majority of the telescopes will be in South Africa and Australia. It will need 2 supercomputers to handle all the data. In South Africa, there will be 197 radio dishes and in Australia, over 131,000 antennae. Each year, SCA will amass 600 petabytes of data, or 1.6 petabytes per day, or approximately 630 Netflix videos a day. To store this data on an average 500 gigabit laptop, you would need more than 1 million of them every year. 500 gigabits is the equivalent of 500 lorries full of paper. To Americans, lorries are trucks. But why does the SCA need such immense computing power? Scientific image and signal processing for radio astronomy consists of several fundamental steps, all of which must be completed as quickly as possible across thousands of telescopes connected by thousands of miles of fiber optic cable. The computers must be able to make decisions on objects of interest and remove data which is of no scientific benefit, such as radio interference from things like mobile phones. What about all the rest? Then, of course, there are the telescopes, observatories, and satellites that are already working. Perhaps one of the most famous is the Hubble Space Telescope. Hubble transmits about 120 gigabits of science data every week. That would be roughly 1,097 meters, or 3,600 feet, of books on a shelf. Hubble has been operational for 30 years and has made over 1.5 million observations. It's not just about the data. To get that, you need to schedule observations. This can be incredibly complicated. Timing, location of object, position of spacecraft, rising and setting times, and many other variables have to be looked at. To organize observations and timings, Hubble uses Spike, which uses a very fast neural network-inspired scheduling algorithm to achieve performance humans can only dream of. We may not have smart cars or personal robots, but advances in artificial intelligence are already providing profound benefits and discoveries for us all. AI is not our master. It can only learn based on how we program it and what we determine as important, at least for now. About the contributor, Patrick Kiernan, Education Demonstrator, Learning and Participation. Okay, so there you go. And, well, I'll go ahead and we'll tour this homepage a little bit. These are, I believe, online museums you can go to and check out. There used to be anybody remember the virtual reality videos? It's just like virtual reality tours of museums, like Versailles. It was actually pretty cool. I don't know if they still see. See if they got anything like that. See this. Okay. This is old, but I don't remember. This is, if you're still listening, the article's over. I'm just doodling around on the internet right now. Okay. Yeah, okay. So they turned it into an app. It used the virtual reality thing. Used to just be a site unto itself. Anyway, so I think that's pretty cool. You don't even have to fly to France. You can go mess around in Versailles if you're so inclined, which is, King Louis's estate of decadence, and we're better than everybody. I'm sorry, that's not correct. Anyway, yeah, so, okay, the article's over, and I need to stop this and go. Thanks for listening. If you did, bye.